Good afternoon. I'm Lionel Marraffa. I'm working at ESA's technical establishment in Dijk, the Netherlands, and my function is aerothermodynamics engineer. I am mostly working in trying to understand and predict the behavior of fluids under different conditions. In general, fluids can experience a lot of physical phenomena that have a large influence on the vehicles that we are developing and studying at the agency. Here, more specifically, if we are looking into capsules and re-entry of capsules, the important process is heating. We have a flow which is very energetic, very fast with respect to our vehicle, or if you prefer, when the vehicle goes down, the vehicle is very fast with respect to the gas, and the vehicle is trying to use the molecules of air around to brake. So it's abandoning its kinetic energy, converting it into heat, into the surrounding air, and trying to evacuate as much heat as possible in the flow. Now, of course, these exchanges are very important to predict, because just a small misprediction could translate into burning the whole vehicle. So there is a number of investigations that are required to define the heat shield that will protect the vehicle during its entry and to size it properly. For the gas flow, what we are talking about is a very high velocity when you have an orbital entry. You can imagine, for example, you have a vehicle coming from the space station entering the Earth. Its velocity will be almost 8,000 meters per second. So it's a huge quantity of energy that you will have to dissipate. In this situation, what will happen is that a very strong shock wave will develop just to adjust the state of the gas to the presence of the body and to bring the gas to rest in front of the body. And during this very strong slowdown of the gas, you'll have a huge compression, and this compression is accompanied by a rise of temperature which is quite dramatic. You could reach more than 6,000 degrees inside the gas near the body. And this 6,000 degrees, to give you a representation, is the surface temperature of the sun. So it's something very high that you have to cope with, and there is no material on Earth that could survive these temperatures if it was completely at the same temperature as the flow. Fortunately, nature is helping us. The exchange is not perfect, so the heat that is contained into this gas, this compressed gas, is not completely going into the vehicle. There is only a very small fraction of this heat that is going into the vehicle. But it is very important to know how much of it is coming, because depending on this fraction, we'll have access to one type of material to cover our vehicle or another. So here you have an example of a conventional stiff technology. You see a typical thickness would be a few millimeters, but it could be much thicker. If you look at the Apollo shields, it's much thicker. And you get to a design that has an inherent stiffness. You cannot change the configuration easily. It's big, it's heavy, and it's expensive to launch and to recover. So the idea came up very quickly about inflatables. You try to have a brake as big as possible. This way you distribute the energy, and this way you brake more effectively. With the stiff technology, you are limited by the fairing of the launcher. With an inflatable or deployable shield, you could have a very compact capsule at launch or at storage in a station, for example, and deploy it only when it's useful, when it is ready to enter the atmosphere. This sample is very typical of a construction of a possible flexible vehicle. You have these N layers, 2, 3, as many sheets as you need, as long as you keep the flexibility required, of course. And this flexible layer is actually a silicon cloth covered with some phenol, silicon phenol. The silicon phenol is an ablative. It will burn and absorb the heat by burning and limit the heat increase. Under that you have packaged a number of multi-layer insulation sheets separated by fiberglass to avoid their collapse in vacuum, to keep them functional and to use them in a re-entry condition. And these multi-layer insulations are very light, and they bring the temperature from the back temperature here, that could be as high as about 200 degrees or 250, to an acceptable temperature at the level of pneumatic envelopes, so that you can keep the air in a good condition, airtight, and you keep your structural integrity. This is of course not really the way we would build it, because you have a strong structure and some measurements devices, thermocouples, because of the needs of the test. But in practice it's a good illustration of how we would build a capsule. IRDT was a joint project where ESA, the European Commission, with their ISTC program, International Science and Technology Center, Astrium and Babakin Space Center in Russia joined their efforts and resources to design, build and fly a capsule. And this first capsule, the IRDT-1, was under the heritage of the Russian penetrator that was developed for Mars 96 mission. They developed a penetrator for Mars entry, and the first IRDT-1 was an evolution of this design for Earth entry. This was in February 2000.
All right, I'm here. Thanks. Bye.
IRDT-2 is going to be an evolution of IRDT-1, going closer to orbital condition. It will be at a speed of above 6.8 kilometers per second versus the 5.5 of IRDT-1. Movie here presents the whole scenario of the IRDT-2 mission. This mission will happen next July. It involves a launch from a submarine in the Barents Sea with a Volna. Volna is a reconverted missile. Here you see the Volna deployment. First the complete vehicle, then we'll have a separation of the first stage, separation of the second stage, and the capsule is deploying here, and you see the deployment of the antenna as well. There will be a GPS on board to track it down. This is the first stage only open. There is a stage open for entry with a high level of thermal protection. You see here the first stage of first step of the entry. You have a plasma formed with a lot of radiation emitted, also invisible. waves, and then when it is cooling down, we can open a second stage, which acts like a parachute, and which is bringing you to the terminal velocity, to the proper conditions at impact. This is here the landing on Kamchatka, and this is typical low velocity landing. We're intending to land around 15 meters per second. It's already quite high, but it's still not a very heavy load, because the precious payload is actually also itself mounted on a shock absorbing device. Future development would incorporate also airbags to this concept. I think that the future of inflatables is quite wide. There's a direct application that we can think of being actually studied actively. It's the servicing of a space station. You have a large capability to bring things up to the space station. You can think of shuttle, you can think of ATV and Progress, but to bring things down, the situation is more limited. And economically, it would make sense to use such an inflatable structure, bringing it up with Progress or ATV, for bringing down samples or bringing down equipment. So that's one thing which is really under consideration, something where students have a role to play. And the nice thing working with students is that they don't have the a priori judgment of the engineers that rely on existing databases and try to depart as little as possible from known fields. They can open new avenues